Okay, so still in applications. Applications to physics. Okay, so let x of t be, let's call this the displacement of an object at time t. Okay, so you're all taking mechanics now? Yes? Anybody not taking mechanics?
I'm not taking mechanics.
Okay, but have you done physics in high school?
Yes.
Okay, good. So it's not, so you just need to know the basic kinematic rules, and not even, I think, could manage without. You know what a displacement is, right? The displacement is the difference in position. Okay, so the displacement really is a vector, but we're not going to treat it as a vector here, just as, let's say, just walking in the same direction. So by how much did I advance, basically? Okay, that's all. The displacement is what's my distance traveled. Let's leave it at non-vector for now, for this course. Okay. Then v of t, which is x prime of t, okay, is the velocity of the object at time t. Okay, so the velocity, of course, is also a vector, but in this course, we're just going to treat it as a speed. Okay, so there's, of course, there is a direction involved because it could be left. If it's negative or positive, it means going to the right or to the left. So that's sort of a vector. But let's leave it for now, okay? And a of t, which is v prime of t, which is x prime prime of t, is the acceleration of the object, again, at time t. Okay, simple. Just the definitions. So let's just look at the one of the equations that you get in physics. Okay, I don't know if you remember. If you're doing mechanics now, you probably remember this. If not, from high school. So it's VIT plus 1/2 a t squared. You remember this one? Okay, so basically the displacement at time t is equal to the initial velocity times the time that you were driving or walking or the object was moving, plus 1/2 times the acceleration times the time squared. This formula gives you the position at time t. Okay, given that it started at an initial velocity of vi. Okay, so let's do the derivative. Let's find x prime. So if you derive everything here with respect to t, okay, so I'm gonna write it differently. I'm gonna write it like this. Okay, so dx dt. I'm gonna write it like this because now there's many letters here. So I just want to be sure that you understand that my variable is t. That's why I'm writing it like this. Okay. There's only one variables. Vi, a are considered as constants here. Okay, so that's why I'm writing it this way, to make sure that you identify that Vi and a are constants. So the derivative with respect to t here will be Vi plus 1/2 times a times the derivative of t2, which is 2t. Cross out. And from here we get dx dt equals to vi plus at. Okay, so I'm sure you've seen this formula before. Okay, so this is what we called the vf. So the velocity at time t is the initial velocity plus a times the acceleration times t. Right, you've seen this? Okay, or if you've probably seen it like this, a equals vf minus vi over t. Same thing. If you isolate vf, you get this. Right, you've seen this one, I think? Okay, over delta t, or I don't know how your teacher calls it. Okay, let's find out the second derivative. So x prime prime of t, okay, or d2x dt2, right? We've seen this notation. Will be the derivative of this now, right? The derivative of the derivative. So you're just going to get a, which obviously is the acceleration, like I said here. Okay, in this case, it's constant. It could not be constant, right? The acceleration could change, but I think in mechanics, in your mechanics course, you just deal with uniformly accelerated motion. I think just acceleration constant. Okay, I think. Is there any question on this? Okay, let's do an example. Well, before that, I'm just going to show you what you've probably learned already. Is that if you have a position time graph, okay, and you have an object, I don't know, it starts at a position 0 and then goes like this, who cares? If you wanted to find the velocity at a certain times t here, let's call this t1. So how would you find the velocity at that point? What would you do? You remember?
You would draw a tangent line.
Perfect. Okay, so you remember that the velocity at a certain point on the position time graph is always equal to the slope of the tangent line. Okay, so this here would be v of t1. So the velocity at t1. Okay, and it's of course the slope of the tangent. And now by now, I think we know that the slope of the tangent is of course the derivative. Okay, and that's why up here, v of t is x prime. Okay, v is the derivative of x with respect to t. Good? Any questions? Okay, let me give you a problem that I found in the book. At t equals 0, a diver jumps from a diving board (32 meters high). Okay, so his position at time t is given by, so I have a formula for his position. So h of t, so basically his height, is equal to negative 16t2 plus 16t plus 32. So two questions. First, when does he hit the water? Okay, and two, what is his velocity at impact? So basically when he touches the water. Okay, so two questions that I need to solve in here. So when does he hit the water? So this is when, of course, the height is 0, right? So this is when h is equal to 0. So I have to solve when is h equal to 0. So negative 60, so 0 equals negative 16t2 plus 16t plus 32. Send everything to the left and divide by negative 16. I'm going to get t2 minus t minus 2 is equal to 0. If I factor, I get t minus 2, t plus 1 equals to 0, and therefore either t is equal to minus 1 or t is equal to 2. Is that what you got? Yes? So obviously, t could not be a negative number. So after 2 seconds, right? After 2 seconds, it hits. He hits the water. Good. What does it mean? What does the minus 1 mean? Okay. So basically, I don't know if I could fit a little drawing here. So the guy is right here. This is the water. This is the water. And so the guy is jumping right here. Right? That's what happens here. So go, jumps, and he hits 2 seconds later. So the minus 1 means what? That if he was if he already had a speed here, velocity here, so if he would have jumped 1 second before from the floor and reached this velocity here, that's what would happen. That's why it's minus 1. Okay. How long before should he have jumped from the floor to get right here? Okay, you get it?
Is it okay if I use the quadratic formula?
Of course.
Okay.
Just longer, but of course, why not? Use the quadratic formula with the 16 and everything?
Yeah.
Okay. Well, you have to get used to recognize that you could factor out a 16 and recognize that you could factor out the trinomial here. It's much, much faster. You know, save so much time. Okay. So what is the velocity at impact? So basically what we're looking for the velocity when at the impact, so when t equals 2. Is that okay? You get it? We said that the impact occurs at t equals 2, and we want the velocity at impact. So we're looking for v of 2. Okay, but v of t is equal to, we said, the derivative of the position, h prime. And so what is the derivative of h? So I think we're good at this now, I hope. So negative 32t plus 16. And so the velocity at 2 will be equal to, you just plug in 2 in here. So negative 32 times 2 plus 16. So you get negative 48. Okay, basically meters per second. And so here's your vector. So since it's negative, means that he's going downwards. And it makes sense. Okay, so the minus here is what represents the direction of your velocity. So this is what makes this into a vector. Are there any questions before I move on to the next topic? All good? I don't want you guys to say that I'm going too fast, taking my time.
Are we gonna have more practices later?
Excuse me?
Are we gonna have more practices later?
Yeah, I'm going to give you practice on this. Yeah.
Okay, perfect.
Now you don't have practice yet because of course we're just, the exam is just done. So it's completely new material. I need to get a bit of material so that I could give you examples, okay? Okay, let's move on. So I'm just going to remind you what, just put up our little plan here, okay? So what we just did, this is done, differentials, and now this is done, applications to physics. Okay, so at this point, what I'm going to do is I'm going to do optimization right now, and the extreme value theorem. Okay, so I'm going to do first the extreme value theorem right now, and optimization. I think I'm going to do all the theorems first. So, okay, so let's start by doing all the theorems, might as well. Okay, they're a bit annoying, so let's get this out of the way. Okay. So the extreme value theorem. So first, let me give you some definitions. Okay. So first thing, a function f has what we call an absolute maximum at C if what? If f of C is greater than or equal to f of x for all x in D, okay? Or D, of course, D is the domain, you all know what the domain is, of F. Okay, so let me get you used to the mathematical notations, okay? Notations, so this for all, we use this symbol. You've seen this symbol before? You've never seen this? Okay, so this is another way of writing for all. Okay, so we're going to use it from now on because I'm very lazy and I like symbols. Okay. All right, so this is what it means that a function has an absolute maximum at C. Okay, so if f of C is bigger than all the values of the function, no matter which x you take in the domain. Okay, and f of C, of course, f of C is called so we call this the maximum value Okay, so there's just a bit of writing now of f on D. Okay, so this is for the an absolute maximum and the maximum value. So we're going to do the same thing with minimum now. Okay, so f, so a function f has an absolute minimum at C if what? Can you tell me?
If f of c is less than f of x.
If f of c is, sorry?
Is less than f of x.
Less than or equal to. Okay, so if f of c is less than or equal to f of x, and for all x in D. Okay, so I'm using the new notation here. Okay. Okay, remember this is for all. You're gonna use this a lot if you continue in math. Okay, so again, D is still the domain. And f of c is called the absolute minimum of f on D. Okay, good. All right, last definition. Well, for now, the maximum and minimum values of f are called so these are called the extreme values of f. Good. So maybe a little picture before I go on to the relative or local. Okay. Are you okay? One more time. I see some of you are still writing. Okay. So just a little picture. So let's say I have a function like this. Okay, so a function defined over an interval a, b. Okay, so of course this will be the maximum, and of course this will be the minimum. Okay, obviously. So I'm going to write this, that this is called absolute maximum. This is the absolute minimum. Okay, and here, and here. This is the maximum value. And this is the minimum value.
Sir, before you wrote FC is called the absolute minimum of F on D. And then you just wrote that it's called the minimum value. Is it the same thing, or is it?
Yep.
Okay.
Oh, no, this I wrote minimum value. Yeah, this should be called the, yeah, you're right. Instead of writing the absolute minimum, actually the minimum value, you're right. It's here the problem. I wrote it here, I didn't write it here. You're right, minimum value, thank you. Right? That's what you're saying?
Yes.
Okay, perfect, thank you. You're right, this is supposed to be minimum value. Okay, and these values here are the extreme values of F, okay, which is basically pretty much the range of F, okay, the lowest value to the highest value. Questions?
Sir, I don't really understand what like F, C, and C are.
You don't understand what?
F, C, and C are.
F, C, and C. So this is C. This is C. And this here is F of C. You understand? Same here. I should have called it another letter, another value. Let's call this C1, F of C1, and let's call this C2, and this is F of C2. Do you understand?
Yeah, but like I don't get what like it means when like FC has to be like smaller or bigger than F of X.
Good. Okay. So it means that I have a certain value here, F of C. Every X that you're going to take in the function, here, 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 for any X that you take here, if you go and you find the value of F, oh, it's going to be lower than this one. If you take another one here, oh, it's going to be lower than this one. They're all going to be lower, no matter how, whatever X you take, it always falls lower than this. Did you understand this?
Yes, thank you. And so that means that there's only one, right?
It means
Like
that
there's only one absolute maximum, one absolute minimum, right?
okay, we'll talk about that. We'll talk about that. Sometimes there's none. Sometimes there's no, right? If the function would have kept going here forever, then there's no maximum. It could happen. Okay. So I have a question on the chat. What is the difference between local and global? Okay, so we didn't, I'm going to teach you local maximum right now. Okay. So this, what we're doing now, this is actually, some books call it a global maximum also. Okay. I call it absolute max, but you could call it a global max or a global min instead of an absolute max, absolute min. So let me show you now what is a, on next page. What's a relative extremes or local extremes, okay? So a function f has a, so we call this a local maximum. Okay, or also you could call this, or it's called also relative maximum. At C, if f of C is greater than or equal to f of x, Okay, so this is a bit more delicate here. When x is near, okay, so near, I'm going to put like this, C. Okay, so this is already, it becomes a, when we're talking about near, it becomes a concept of topology and analysis, which you do in more advanced math, but I could give you the idea. Okay, so what does this mean? Okay, what does near mean? So I'm gonna write like this. For some open interval containing C. Okay, and this is a bit complicated. I'm going to try to explain to you with a little picture in a minute. Okay, let me just do the equivalent for the local minimum, and then I'm going to explain to you. I'm going to try. Okay, so the difference between the absolute and the local, the absolute was just so you see it. So I'm going to remind you. Okay, so the absolute maximum was for all x's in the domain, for all. And here, it's not for all, it's just for some open interval around C. Okay, so containing C. We'll talk about this in a minute. A function f has a, so let's do the same equivalent definition. So local minimum, okay, or we could also call this relative minimum. At C, if f of C, of course, is smaller than or equal to f of x, when, again, x is near C. Okay, so near means, again, the same thing. Okay, so let me try to express this with a little picture. So here's a function. Okay, so it keeps on going forever, keeps on going forever. But right here, at a certain value C, I could find a little interval around C, okay, where the function is always everywhere in this interval. You see that the function is under this value. This here is a local maximum. Do you understand this?
Can you repeat it?
Of course. Okay, so it's a local maximum at C because I could find sort of a little neighborhood. Okay, so neighborhood is a very specific mathematical word. Okay, so a neighborhood around C. Okay, where all the values of x taken in that neighborhood, okay, the value of the function of these values is always going to be less than a certain value here, which is f of c. Do you understand?
Yeah, but why is it like not
Absolutely.
like, yeah.
Okay, because, very good question. Because if I take an x here, I'm bigger.
Okay.
Okay, so so absolute maximum means he's the maximum overall, he's the king of the world.
Mhm.
Okay, but a local maximum means he's just the king of his little region. Okay, so he's a local, he dominates locally, but he's not God.
Okay.
You
Yeah.
understand? You understand?
Yeah, I get it. Thank you.
So there's always, so right here, he thinks he's the best, but if you go a bit further in your function, there's somebody better than him. So he's good locally. Okay, so around him, everybody looks up to him, but people far from him look down to him. So he's just a maximum locally. Good?
Yes.
Okay, so same thing for the minimum. Okay, so again, here, we have a value c. So at a certain neighborhood around c, okay, he's the lowest. There's nobody lower than him in his neighborhood. So he's a local minimum. Okay, so he thinks that this guy here thinks he's the worst there is, but there's worse than him. There's lower than him, if you look further.
Are we able to make the interval as big as we want as long as it's like lower than it, or if it's like above it, like it could be as big as we want as long as we don't?
Okay, it's a very good question. Okay, so I would say, we make it as big as we want? Of course, if you make it bigger, then he's not the minimum anymore. There's a certain place where you're gonna start including these values here, which are lower than him. You understand?
Yeah.
Okay, so the question is, could we take the interval as small as we want? That's what you're saying. Okay, because if I have a function that's like this, I'm gonna write here. Let's have a function that's like this. So I mean, could these be considered a local maximum? That's what you're asking, I guess. Or I don't know if you went. I'm gonna draw it a bit better because this is really not nice. But if my function was like this, okay, so I could ask myself, is this a maximum or not? Well, it seems that it is, because I see that I have a sort of a summit here, okay? But how do you express it with what we just learned? Well, is that if this is C, well, I could find a certain neighborhood, a very, very small neighborhood, where he's the highest. Do you understand? Well, every value of x here, the f of x will be smaller than f of c. Do you understand what I just said?
Yeah.
Good. Okay. It's like if the guy is the king of he found 3 people and he dominates 3 people and he thinks he's the king of the world, but then he goes out to see 5 people and then he finds somebody bigger than him and then it's finished. You understand? He's the maximum locally, but not absolutely. Is that okay? I'm trying to explain to you with jokes, but this is serious stuff, okay? Is this okay? Let's move on. Okay, let's leave this for now. Okay. So let's go with the extreme value theorem. So this is serious. Okay, so our first big theorem. move up here. All right. So if f is continuous, on a closed interval, let's say AB, then f attains or reaches an absolute maximum value. So let's call this f of c. And in an absolute minimum value, let's call this f of d. Okay, at some numbers c and d in the interval AB. Okay, so this is a very important theorem. We're not going to prove it because it requires some advanced concepts. Okay, but you have to understand it. So let me just, I'm going to box it. Okay, so let me just draw something here and try to represent this theorem with a little picture. Okay, so here's a function over AB. Okay, so what the theorem tells me is that if the function is continuous, then for sure, there is a maximum value and there is a minimum value to that theorem, to that function. It attains the maximum value and it attains the minimum value. Very important theorem, okay? And you have to understand it well, not just memorize what I'm doing because you're not doing anything, okay? So this, I'm going to spend some time on it if you want, more time. C, D, so in using the same letters as I used in the theorem, this would be f of C, and this would be f of D.
Sir, can you move up the paper a bit?
Move up.
Yes.
You can see the bottom.
It's dark.
Is it better?
It's just not really clear.
What's
On the letters at the bottom on the x-axis.
okay? So it's A, C, D, B.
Okay.
Well, maybe I should write that bigger. Actually, yeah, I see on the screen now that it's not. It's a bit small. I'm writing this. A, better.
Yes, thank you.
Okay. A, C, D, and B. Okay, and that's F of C, F of D. Okay, so it's a very, very important theorem. What it tells me is that if I have a function that is continuous over an interval AB, well, it's for sure going to reach its maximum and for sure going to reach its minimum.
Hey, sir.
Yeah.
What if it's not like a closed value, a closed interval function, but rather it's a function that repeats itself like a sinusoidal function?
Over an interval?
Yeah.
Over a closed interval, on a closed interval. But I don't understand what your question. The fact that it's a sine function, I don't care. Why does it change anything?
Like if the function just repeats itself over and over again, is that like the same? Will it also have an extreme value?
Of course. The requirement is that it needs to be continuous and it needs to be on a closed interval. That's it. This is my requirement. Okay, on the closed. Okay, so continuous over a closed interval. Okay, so let's see why do these requirements need to be here? Why does it need to be continuous and why does it need to be in closed interval and not in open interval? Okay, let's see a bit deeper. Okay, so I'm not going to write it here because it's too small. I'm going to change page. Are you done writing? Okay. Let me write this down. The continuity requirement is very important. Okay, because as you'll see, if my function is not continuous, then there's no guarantee that my function will reach a maximum value. Let me give you an example. Actually, you could also give me an example. It would be best for me if you could find the example instead of me. Okay, so let's try to find two functions, okay, on AB. Okay, so closed interval, but that the function doesn't reach a maximum value. Can you give me that? Can you find? Can you think of an example? The easiest one would be a function like this. So it starts at A, let's say it finishes at B here, who cares? And it goes like this. There's an asymptote, and then there's an asymptote. There you go. The function is defined from A to B. Okay, and let's say here there's just for the domain to be AB. So there's a point here, let's say, who cares? But as you see, the function is not continuous. So there's no max, there's no min. You understand? That's one example where we have a vertical asymptote in the middle or somewhere in the interval. Questions? Is anything not clear? Is the concept not clear? Anybody want me to repeat?
Please, can you repeat one more time?
Yeah. Okay. So what I'm saying is that, again, I'm going to go back here. Okay. So what I wrote here is that the extreme value theorem tells me that if a function is continuous over an interval AB, closed interval AB, then for sure the function reaches a maximum value and reaches a minimum value. Good?
Yeah.
Now I'm
thanks.
questioning, why did it tell me continuous? I don't care about continuous. Leave me alone. So I'm giving you an example of a function that is not continuous. And I'm saying, oh, 1 second. If you don't tell me that it's continuous, then I could come up with a function like this that is still defined on a closed interval AB, right? Every x in AB has a value of the function, right? But there's no maximum because you see here it goes to infinity and here it goes to minus infinity. There's no maximum, there's no minimum. Do you understand?
Yes.
Sure?
Yes, sir.
Okay. Let's think of another case where there's no asymptote. Can you think of one? Can you give me a case where the function is defined on a closed interval AB? There's no asymptote, okay? But there's no maximum and no minimum. Can you come up with this? If you could come up with a function like this, it means you really understood.
Maybe a constant
Okay,
or a
that's
straight
good.
line.
Good. So you say a constant function, flat?
Yes.
Well, there's a maximum and there's a minimum. Every
But then-
value on the interval will be a maximum and the minimum at the same time.
Okay.
Okay?
What about like a linear line, like a straight line?
A what? A straight line?
I guess like a linear line, yeah.
Like this?
Yeah.
So the minimum is here, maximum is there, no problem. Right? Anybody?
A function with a removable discontinuity.
Oh, good, good, very nice. So a function with a removable discontinuity, so maybe something like this. Like this, you mean?
Yeah.
And maybe like this. And like this, let's say. So here's a function. So it's defined from A to B, right? Every value from A to B works, but there's a discontinuity. You said removable, okay, I'm doing a jump. But with a removable also it would work, it could work. But here I'm really giving you an example that there's no maximum and there's no minimum. Okay, so even if this was, let's say, 2, so it's true that 2 is it cannot exceed 2, but it will never reach 2, and so there's no maximum. Okay, so this is already a concept of upper bounds and least upper bounds and maximums, and okay, let's leave for now. This is not in this course. Is this clear?
But then wouldn't the maximum and the minimum be the value that's like just before that jump instead of like yeah, it doesn't exist there, but maybe it's like the value right before the line like goes straight down.
Right before, like, let's say this is 2, let's say. So it would be what? What right before 2, you mean?
Yeah.
Like what? Tell me. What's right before 2?
Well, I'm not sure, but like we were just working on the limits, so like 1.999, like very close to that.
Yeah, close is not a number. I need a number.
Oh,
I need
okay.
a number. So you know there's no number right before 2. It doesn't exist.
Oh, okay.
Okay. Okay. Good. But these questions, right? These questions of what it's right before 2 and things like that. Okay. This we're talking, this is more advanced stuff. Okay. Okay. So that's for the continuity requirement. How about the closed interval requirement? Okay. So the closed interval requirement is also very important. Okay, so let's say, so let me draw again another function and give me an example where the interval from A to B now is open. Oops, sorry. A, B. So now the function, let's say, is continuous, let's say, but is defined on interval AB and not including A, not including B. Can you give me a function that for which it won't reach a maximum or a minimum, or both? Go ahead, I'm waiting, I'm listening.
Well, if the function is a linear, then there could be no minimum or no maximum because it goes on forever if there's no closed interval.
No, but I'm still over AB.
Oh, okay.
It's still over AB, but A and B not included.
Could it be a function with a horizontal asymptote?
With horizontal asymptote? No, why not necessarily? I mean, horizontal asymptotes are effective when you're at close to infinity or minus infinity. Here, I'm just on AB, so there's no horizontal asymptote in effect here. Okay, so you don't have much time. So I will just do it for you. A simple one will be just a function like this. Not including here, not including there. So the function is continuous, but as you see, there's no minimum, there's no maximum. Do you understand this? Okay, no questions? Okay, I'm going to stop here. I'm going to stop here for today. Okay.